Okay, welcome to the first set of parallel sessions at QIP. We're going to have one talk and then we'll have a break. During the break, coffee will be available downstairs on the first floor, but we will not have coffee available on this floor, so you will need to go down and then hopefully come back up because there's two great talks after the session, after the break. The first talk in this session is by Anna Komar, Olivier, Landon, Cardinal, and Kristan Temme. It's an energy barrier is necessary for the thermal stability of stabilizer quantum memories. And today we have Anna from Caltech giving the talk. Please welcome Anna.
Thank you. I wonder if everyone can hear me, or should I place it? Everyone can hear me? Good, perfect, thank you. So this is actually a merger of these two papers mentioned here. And so this is our main result here. What we did is we investigated these two classes of models, the commuting Pauli stabilizers and Abelian quantum doubles. And essentially we were interested in whether these would be good quantum memories in the sense that whether they have self-correcting properties. And so we modeled the thermalization of these models by a Liouvillean. We lower bounded the spectral gap of that Liouvillean, which then implies an upper bound for the mixing time shown here. So the mixing time in this context is akin to the thermalization time. It just means that any state of the system is close to a Gibbs state after this amount of time. And so the bound is in this form that we acquired. There's this n square, which is just a constant polynomial factor, so that's not super important. What's more important is the exponential to inverse temperature epsilon bar, where the epsilon bar is the generalized energy barrier that we properly defined. And so if you look at the form of this formula, you can see that depending on whether the energy barrier scales with system size, if it scales with system size, then this upper bound allows for self-correction of that model. And if the energy barrier is a constant, then self-correction is ruled out. Also, if you're familiar with the Arrhenius law, then you can observe that this formula, this upper bound, is very much like that. So with that, here's the outline. I will first talk a little bit more about the motivation, why we did this work. Afterwards, I will show you the models a little bit more in detail, and I will talk about the noise model we applied. Then I will talk more about this thermalization time bound. I will define the energy barrier. I will show you how to evaluate that barrier for several models. And then at the end, I will show you a couple of steps towards the proof. So as I mentioned, we're talking about quantum memories. So a quantum memory is just a physical system you encode your information in. So it's good if it has degenerate ground state. It should be robust to perturbations. And it should have a long memory time. What you mean by long can depend on several things. One of these things is if you're fine with applying active error correction, then it doesn't have to be that long. Active error correction means that you encode your information, and while the information is there, you continuously do syndrome measurements. And based on the result of those measurements, you either just keep track of the errors that happened, or maybe you correct for them immediately. But the important thing is that you do this, and at the end, you decode. While self-correction would be a little bit more ideal, this means that you encode your information. You just wait that information stays there, even in a thermal environment. And then at the end, you decode. So this long time you wait could be a bit more precisely defined. What we mean here is that if this time you can wait scales exponentially with system size, that's the best. That's what we mean by self-correction. And so that's what we set out to answer, whether these models have a property like this. So you can talk about thermalization of models by this phenomenological picture called the Arrhenius law. This essentially tells you that the memory time of systems, or the thermalization time, scales with exponential inverse temperature some energy barrier. Here the energy barrier is once again kind of phenomenological notion. If you look at the picture there, it's shown there what we mean by that. So there is a state psi you encode your information in. But then, of course, this is in a thermal environment, so the environment will apply some errors which might move you out of that state, and eventually you might end up in an orthogonal ground state. So that means your information is destroyed. And so when these local errors are applied, you go through an energy landscape, and so essentially the highest barrier you have to pass in this energy landscape is what we mean by the energy barrier. So if you look at the Arrhenius law, you can see that there might be some connection between a scaling or constant energy barrier contra self-correction. And so if we really take this seriously, then you can see that if you have a constant energy barrier, then your memory is not self-correcting. You just have a constant time. And also, if your energy barrier scales with system size, then your memory can blow up. So two examples for this are the two-dimensional and the four-dimensional toric code. So these both obey the Arrhenius law precisely. While you can talk about a different model called the welded code, which even though it has a scaling energy barrier, its memory time is constant, essentially. So that's a little bit surprising, but not that surprising. You can think of, in this case, the Arrhenius law as some upper bound. So even though there's a scaling energy barrier here, which would allow you to have a huge memory time, but the welded code just doesn't live up to that possibility. So these are all these models all in a sense obey the Arrhenius law. But if we were to have something there called entropic codes, which in our case would have a constant energy barrier but still have self-correcting properties, that would be surprising. So the idea here is that even though your energy barrier doesn't scale with system size, you might have entropy on your side in the sense that it might be easy to overcome just one energy barrier somewhere on your landscape, but maybe that path is not typical, so entropy comes to your rescue there. And so there's one suggestion by Brown and others, where they essentially did simulations for the Abelian quantum double model, a modified version of that. And they've seen some improvement due to their modifications. So that's a hint that there might be something called entropic protection. And that's another thing we wanted to think about. But this picture is very phenomenological. So we're sure that you can do better than that. You can probably talk about the dynamics. So if you want to talk about the dynamics of thermalization, then what you do is you have a Liouvillean, which is just an operator that, a details balanced operator that drives any state towards your thermal state. And so you model thermalization with that. This Liouvillean has a spectral gap of lambda, which in this case is important because with this lambda you can bound the mixing time. So essentially n over lambda in this case is an upper bound. And just refreshing, so mixing time again is the amount of time it requires for your state to be close to the Gibbs state. So if this is what you do, then Alitzky, Fanes, and Hordetsky derived a lower bound for the spectral gap. This is what they got. And so, as I mentioned, this implies a mixing time bound, which is in this form, n times some exponential. But what's important here is that this exponential is essentially just a constant if you think about the system size. So this is one way to see why the two-dimensional toric code is not a good self-correcting memory. And another thing important here is that, so we talked about the dynamics here. You can go through this, you can get some bounds. But there's no place here where the energy barrier appeared. While in the previous slide, if you remember, I talked about energy barriers and some phenomenology, but there was no dynamics involved there. So one of the things we wanted to answer is whether you can come up with something which connects your energy barrier and the dynamics of thermalization a bit more rigorously than what we have so far. And another question is, which might be answered if we answer the first one, is entropic protection possible? If you have a constant energy barrier, could you still have a good self-correcting memory? So these were our objective. And so let me talk about the models we investigated. One of these models are just stabilizer codes, Pauli stabilizer codes. just so we're on the same page, here you have a Hamiltonian with local terms, and these generators in local terms are commuting Paulis. Everything commutes with each other. On the side, you can see an example of the two-dimensional toric code, where these generators are just the star and plaquette operators, Pauli z's and x's in this star and plaquette geometry. And so these generators generate the stabilizer group for you, which then has a code space defined by stabilizer acting on states of the code space, leave the code space invariant. And then you can define your logical operators, which are in the toric code case are just Pauli x's and z's that wrap around the torus in these non-trivial loops, in the non-contractible loops. So this is one of the types of models we looked at. And then there's the other type called Abelian quantum doubles, which are defined on a two-dimensional lattice. And so this is essentially just a generalization of the toric code, where instead of qubits now you have qubits on your edges. So what you then need to do is generalize your Pauli operators. And with these generalized Pauli operators, you can have generalized star and plaquette operators, which once again are required to all commute with each other. So if you have these star and plaquette operators, the next thing is you might be interested in what is the Hamiltonian. So you can define projectors with these star and plaquette operators, which essentially just project to the different subspaces corresponding to different roots of unity in this case. Or if you want to be a bit more physical than that, you can say that they project to having different excitations at different vertices and plaquettes. So with these projectors, P and Q, where P is related to the star and Q is to the plaquette operators, you have your Hamiltonian here in this form. So this is the other type of model we looked at. And then the noise model we applied is the following to both of these models. You have your system Hamiltonian, and then there's a bath connected to that system. The connection between them is given by an interaction Hamiltonian in that form, where the S alphas are operators applied by the bath onto the system locally to either just one qubit or qubit. And this is essentially your interaction. The total Hamiltonian is then system Hamiltonian plus interaction Hamiltonian plus bath Hamiltonian altogether. And so if you want, yes, there's a question.
Is this just the boundary or all the qubits?
Oh, you mean the S alpha, whether that only acts on the boundary or all? No, it could act on any of those, any of in the bulk. So with this complete Hamiltonian, you can evolve your system. Then you trace out the bath, and you get your system Hamiltonian. If you further apply some approximations, the Markovian limit and the weak coupling limit, meaning that the interaction is small, then you arrive to the master equation in that form. So here, this L symbol is the Liouvillean, which in our case is this Davies generator form, where it's kind of complicated, but there are not too many symbols in here. So there's H, and then there's S. So the S alpha omegas are just the Fourier transforms of the S alpha operators I showed you a minute ago. So essentially, if you apply an S alpha omega onto a state of the system, then it jumps into another state. The energy of the new state compared to the previous one is just an omega difference between them. And then there's H alphas, which are the transition rates corresponding to these S's. So there are some requirements that if are satisfied for S's and H's, then this Liouvillean will be a good model of thermalization in the sense that it drives any state towards the Gibbs state. So this is the noise model we applied. And so with that, we have every component for us. So we have this, the systems we looked at. We have the noise model. So let me show you our result a bit more in detail. So again, just so we know what we're talking about, the mixing time here is the amount of time it requires for your state to be epsilon close, where epsilon is a number, to the Gibbs state in trace norm. And then with that, our theorem says that for n-qubit Paulis or n-qubit Abelian quantum doubles, the mixing time is upper bounded by this formula, where the n factor is again just a polynomial, not very important. Here you have mu star, h star, and epsilon bar as constants. So mu star and h star are again, not super important because both of them can be upper or lower bounded. Mu star is at maximum something which scales with system size, and H star is just the smallest transition rate, so that could be lower bounded. What's actually important here is the energy barrier epsilon bar, and if you think about this a little bit, you can see why it's the one important. Because everything before is just probably gives you something maximum polynomial, while epsilon bar is inside the exponential. So if epsilon bar were to scale with system size, that gives you a huge upper bound, which could allow for real self-correction. While epsilon bar, if epsilon bar is a constant, then you have a small upper bound and self-correction is ruled out. So this is essentially the result, although I should probably tell you what epsilon bar is at this point. So I will show you that through an example. So here, let's think about the two-dimensional toric code. And what we need to do in order to understand what is the energy barrier is, for now, think about any eta f error configuration that the environment might apply. Any, it doesn't have to be logical. So let's think about this one there. There are some z operators applied at certain qubits. Then what you need to do is look at this error configuration and find which plaquettes, or maybe star terms, are violated. By violation, I mean that the plaquettes or star terms there anti-commute with this error. So you can see that the gray plaquettes here are violated. Everything else is fine because the first z just wraps around the torus. So then, after we located these, we throw these out of the lattice, meaning that there will be essentially holes there. We don't care about these plaquettes anymore. So afterwards, what we will do is we will construct this error here. We'll construct this error by applying local operations one after another. So first, let's say if we first apply the z operator there. And then what we'll do is we'll locate which plaquettes are violated here. Well, there are two of these, one up and one, so like one above, one below here. So what we will do is we will count these violations. There are times two. If you apply another z operator, one of the violations moves a little bit, but it's still a 2 violation. And you can continue this until if the whole logical operator wraps around, this will give you a 0 violation. But then you might start applying another z towards your final error there, which, and this point is actually really interesting because that z there should violate both the plaquette to its left and both the one to its right. Why I only colored the one to its left red is because we've already thrown out the plaquette to its right. So we don't care about it anymore. That's what we did in the second step. So then this gives you a violation of 1, and then you finish this whole procedure and you have your error. So what we did here is, while constructing this error, we counted how many violations we have. We maximized those violations, which in this case were 2. And that's almost your energy barrier, except you could have chosen any kind of ordering to place down these z operators, right? I chose this kind of logical thing, but I could have done anything else. So then you're allowed to choose an optimal ordering in the sense that it's fine if you minimize the energy barrier by this ordering. What I showed you was actually the minimum. And then if you do that, you get your epsilon bar eta f, which is the energy barrier corresponding to this specific final error configuration. Now, for this specific final error configuration, so now what you have to do is consider any and all error configurations you might think of and maximize for those. That's your real energy barrier for the 2D toric code in this case. So if you really think about this, what we've got here for the toric code is an energy barrier of 2. So that kind of means the same thing as we've known before, that the upper bound for the mixing time is at maximum exponential beta some constant. So this is not a good self-correcting memory. But another interesting thing is why, like, it was in a way easy to find that the energy barrier is 2 here. There were just only so much simpler errors you should think of. There are some loops here, there are some strings here. That's most you can have, because they're just one type of excitations. Loops and strings are all you have to deal with. While if you want to consider the Abelian quantum doubles, the other model we thought about, instead of just one excitation and the vacuum, you could have d-1 excitations plus the vacuum. So you can imagine that when you consider any final error configuration, that could be very ugly and huge, and there could be all these decays and fusions happening in there. So it's not so trivial to construct such a complicated error configuration with a constant energy barrier. That was our goal. So what we did is we set out to break down any huge, ugly error configuration into very simple elementary structures. And by simple structures, I mean loops and strings, or loops and trees, which very much resemble to what we could already construct in the toric code case. So how we did this breakdown is let's look at this Pauli configuration we have here. Then you can think of this configuration as just having some anyons at the ends. So if you think of that ZZ, the red one, for example, then you can think of that as creating an anyon 1 and 4 up there, and then moving the anyon 4 down all the way down to the end. So this is in d equals 5 now. And you can think of all of the others by creating a pair of anyons, moving some of them. Actually, the below one is a little bit more interesting, because in this case, you create an anyon 2 and a 3 at the far end, and then you start to move the anyon 3. It might decay into an anyon 2 and a 1. In this case, it decayed, and then it continues moving. So the idea is that you can think of any error configuration